Today we will be starting graphing polynomial functions. So we are going to just jump into this warm-up that says to graph the following quadratics. So if they are quadratics, that means they're x squared, which means they look like that, so they're parabolas. And so when they're given to us in factored form, this creates a 0. So where x minus 3 equals 0 is my 0. And another word for 0 is solution or x-intercepts. So I have an x-intercept at x equals 3. And then likewise with the x plus 1, it will give me my x-intercept. So I have another x-intercept at x equals negative 1. And I don't have a negative in the front, so this is a parabola that faces up, but I don't know where the vertex is. Sorry, I don't know where the vertex is. So what we're going to do to find that vertex is we're going to FOIL this whole thing out. Look at x squared plus 1x minus 3x minus 3. I'm going to combine my like terms. I get x squared minus 2x minus 3. Now remember, we find the x value of our vertex by taking negative b over 2a. So negative 2 is a positive 2 over 2 times 1. That's 2 over 2, which is 1. So the x value of my vertex is 1. Then in order to find the y value, I'll plug that straight in. So it'd be 1 squared minus 2 times 1 minus 3, which is 1 minus 2 minus 3, which is negative 4. So my vertex occurs at 1, negative 4. So go to 1 on the x value on the x-axis and negative 4 on the y, and connect those to the vertex. And so that is my first one graphed. We'll do the same thing on number 2. These give us the zeros, and we take the opposite, as we saw that when we had x minus 3, we got x equals positive 3. When we had x plus 1, we got x equals negative 1. So x equals positive 2 and x equals negative 2. So those are my two x-intercepts, but I still need the vertex. So we'll FOIL this thing out. We got x squared plus 2x minus 2x minus 4. X squared minus 4, because these two middle ones will cancel. So x squared minus 4 is my y equals. So I'm going to take x equal to negative b. I don't have a b value, so it's 0 over 2 times 1. 0 divided by anything is 0. So we're going to be on 0 for the x, and then for y we'll plug in a 0. We got 0 squared minus 4, which is negative 4. And so that gives us the vertex at 0, negative 4, which would be right here. There is no negative in the front of those x's, so we are facing up. This should be relatively familiar from when we graphed quadratics, and if it's not, that's okay. Just be sure to go back and look at any of those notes that you might still have to help you. So again, we have a positive, so it's going to be facing up. We have x plus 2 squared, which is the same thing as x plus 2 times itself, which means my 0 is at x equals negative 2. But I only have one 0. If I only have 1, 0, then I can't cross anywhere else, which means my only option is to go up from that point, which means that is my vertex as well. When that is your vertex as well, to find another point, we can find our y-intercept, which would be where x equals 0. So y would equal 0 plus 2 squared. Y equals 2 squared, which is 4. So we would have a point as 0, positive 4, which is right here. If this is also my vertex, remember that is where the axis of symmetry is, so we could reflect across it to find the other point, so that way we can create our quadratic. That is a terrible parabola, I'm so sorry. So now when we're graphing polynomials, that means we have a degree that is most likely higher than just a square. So we're going to be dealing with cubics and quartics and quintics. And so remember we found the end behaviors for our polynomial functions by the degrees and the lead coefficients. So if the degree is odd, remember that means they're going to be opposites. So the lead coefficient is positive, means the last is up. So we'll be up over here. And then we have to be opposite, so we would be starting down. And anything could be happening here. So as x approaches negative infinity, which is down here, then our polynomial would start down. As x approaches positive infinity, it goes up. Then when the lead coefficient is negative, the last is down. So as x approaches negative infinity, we would be up, because they have to be opposites, and down for infinity. So positive infinity is down, negative infinity is up, so our graph would look something like this. And again, anything can happen here. Anything goes, depending on the polynomial that we have. So the one that I'm sketching is very close to a cubic function, but again, we're going to have those quintic and quartic and every other ick on those graphs. So anything goes kind of in that center section. They're not always going to look like a cubic. Now, when the highest degree is even, that means they're the same. So if it's positive, they're both up. So we would have something that looks like that. And if it's negative and even, then we would have something that looks like that, because they would both be down. So we're going to fill out this table with our functions. And this is very similar to what we did when we were finding the end behaviors. So for this function, negative 5x cubed, the degree of the polynomial is 3, which is odd. So let's leave a little more space. And the sign of the lead coefficient is negative. So we have odd, negative. Negative tells me this one is down. Odd tells me they're opposites. On the next one, our degree is the highest exponent that we have, which is a 3 again. So that's odd. And the sign of the lead coefficient is negative. Odd tells me they're opposites. The negative tells me the last one is down. So we have up, down. Now on the next one, they're not in order, so be careful about that. The degree of the polynomial comes from the highest. So the degree is 4, which is even. And the sign of that coefficient is negative. So even and negative, negative tells me the last one is down, even tells me they're the same. On the next one, be careful because it's also not in order. So the highest one is first, meaning this degree is 3, which is odd. And the sign is negative. So we have negative, odd. So it's ending down and they're opposites. On the next one, they are in order, so our highest one is first. The degree is 4, which is even, and it is positive. So positive tells me the last one is up, and even tells me they are the same. On the next one, highest degree is what we're focusing on. Degree is 4, which is even, and it is positive because we don't have a sign up here in the front. So if it's positive, that means the last one is up. Even means they are the same. Next one is a degree of 4, which is even. That is positive, which again is up, up. And here again, the highest degree is first, so that's another 4, which is even. And the lead coefficient is 3, which is positive. So that's up, up. So what will a graph with the following characteristics look like? So if we had a graph with a degree of 5 and a negative leading coefficient, degree of 5 is odd, and this says it's negative, so it will end down and opposite start up. Degree of 6 is even and positive lead coefficient. Positive would mean it would end up. Even would mean it would start the same way, so it would start up. So on this table, we have our lead coefficient, which is going to tell us the last behavior based on negative or positive. The degree tells us the starting behavior. And what I mean by the starting behavior is we have to look at the last behavior first, and then the starting behavior would be opposite or same as end. And that's based on even or odd. The number of zeros is up to n. So remember that the degree is n and the lead coefficient is a. So we can have up to n zeros. So for example, if we had x to the 5th power, we could have as many zeros as 5, but we can't have 6. And then the number of turns is how many times it goes from increasing to decreasing, like that. So we can have up to n minus 1 turns. So again, with that example of x to the fifth, then our graph could only have up to 4 turns. Multiplicity is the number of times that we have a certain zero. So something like x minus 2 squared has a multiplicity of 2. And whenever you have a multiplicity of 2, it will kind of bounce. So that would be a graph that goes down, hits the 0, and turns back around. Multiplicity of 1. So when it's just something like x minus 2. And so it will go straight through. So that would be a 0 that does something like that. It's just going straight through the point. And x minus 2 cubed would be a multiplicity of 3. And that one I like to say loop. Not really a loop, but I like to say that it loops through, because it would be something like that. So it's hitting the 0, but it's not hitting it straight. So it's going to kind of loop through there, snake through there. So we're going to work on this one, and then we will sketch it without actually graphing it. So we're given the polynomial y equals negative 2 times x plus 1 squared times x minus 2 times x minus 3 cubed times x squared plus 2. So determine the end behavior of the graph. For the end behavior, we need the degree and the lead coefficient. How can we find the degree when they're all spaced out like this? Well, I know that this 2 will end up on that x squared times the x in here times an x that ends up cubed, and then another x squared. We're actually going to get rid of this last piece, because this last piece would give us an imaginary 0, and we haven't really talked about those. So we're just going to keep those. So with the end behavior, the degree we're going to find by what we just typed what we just wrote out. So the x squared times the x cubed. That's an x to the 6. So my degree is 6. And my lead coefficient would end up being a negative 2. Because no matter how many x's I have in the front, we're going to be multiplying by negative 2 in the front there. So we have an even negative. So that means my end behavior is down, and since it's even, down. So it would start down and end down. And we're going to determine the zeros of the function. So the zeros, remember, we get from each of the factors. So 1 0 I get from here is x plus 1. We would set that equal to 0. We take the opposite, is x equals negative 1. and that has a multiplicity of 2. We have x equals positive 2 with a multiplicity of 1, and x equals positive 3 with the multiplicity of 3. So those multiplicities are going to come in handy when we start talking about the behavior of the graph at each of those zeros. So then we're determining the x-intercepts. X-intercepts we write as points. So x-intercept is x, comma, 0. And the x-intercepts are the same thing as zeros. So we have -1, 0, 2, 0, and 3, 0. So I just got that from the part B, where we wrote the zeros. Zeros and x-intercepts are the same thing, and it's the same thing as solutions. So they all mean the same thing, but when it is an x-intercept, we write it as a point. On D, it says determine the y-intercept of the function. So the y-intercept occurs where x is 0. So we're going to say y equals -2 times 0 plus 1 squared times 0 minus 2 times 0 minus 3 cubed. So that's y equals -2 times 1 squared times -2 times -3 cubed. So that's -2 times 1 times -2 times -27. So let's see what that is. It'll be 4 times -27, which is -108. So the y-intercept occurs where x is 0. So it would be 0, -108. Now describe the behavior of the graph at each of the x-intercepts. So at x equals -1, it has a multiplicity of 2, so it's going to bounce. At x equals 2, it has a multiplicity of 1, so it's going to go straight through. And at x equals 3, it has a multiplicity of 3, so we're going to say that it snakes through. So then without using a calculator, we're going to sketch the graph of the function. So we have our x-intercepts, -1, 1, 2, and 3. Our y-intercept is 0, -108. It's going to be way down here. And we know that our graph will have to start down and end down. So our graph goes through the x-axis at each of those points. It has to hit the y-intercept, and it has to bounce, snake through, and go straight through. So at x equals -1, it's going to bounce. So we start down. Let's say it's going to -1. I have to bounce back so it can't cross. Then we have to go through 108, then up to 2. It'll go through 2. And then I have to come back to 3 somehow. But I don't know what's going on with the graph here. So I can go up and just at some random point turn around, because remember, this is a sketch. It doesn't have to be accurate. The accurate points have to be our x-intercepts and y-intercept. So now I have to go to 3, but I'm not just going to go straight through. I have to kind of loop and then go down. So this is a terrible sketch because what is this? But we see that it's going to hit 3, but kind of at an angle. So it should look like that if we zoomed in somehow. And then we see that we started down and ended down. So when you're asked to sketch a graph, what we want are the zeros, any intercepts, so the zeros and the y-intercepts, and then the behavior. So the behavior at those zeros and the end. That's what we're looking for. We're not looking for, well, what point is that? That doesn't matter to me. What I want to know is that it goes through 2, but then turns around at some point, and then loops or snakes through 3 on its way back down. So, on the next page, we have this chart here, and I want y'all to do this chart for homework. But I do want to add one thing to it. So add a column here that is a sketch. Remember, it doesn't have to be accurate at all. Excuse me. Sorry about that. So on the added column, I want you to put a sketch of the graph. If you don't have space, obviously, then you can put that on the back of this or on any random sheet of paper. And let's just label them. 1, 2, 3, 4, 5. And make sure there's no imaginaries on here. Oh, this one has imaginary. And this one has imaginary, so this will be 3 and 4. So really you're only going to do those ones because I don't want you to have to deal with imaginary numbers. So 1, 2, 3, and 4, you're going to find the lead coefficients and the degrees. Then you will know the number of zeros. The number of turns, remember it is the n-1. And I'm not so concerned about the number of turns. So just write n-1. So whatever your n is, your degree, subtract 1 from that because that's as many as it can have. It might have less though. So don't be concerned about the number of turns so much. Then the actual zeros and their multiplicity. So remember the multiplicity affects the behavior at that 0. And then I want to see a sketch. Since this is day 1 of graphing, don't worry about your sketches being accurate at all. So just find those zeros, find the intercepts, and then the behavior at those zeros and at the end of the graph, the starting and end behavior. So that's 4 problems for y'all to do for homework, and then we will continue graphing polynomials on Monday.